Okay, so yeah, welcome. So due to power cut, we got delayed today to start this class. So yeah, so in last class we have started our means we were discussing about this propagation delay, and we have seen how to estimate the total input capacitance, output capacitance, right? And now when you want to calculate delay, that is TP, you know the TP is the average of TPHL and TPLH, right? TP is the average of these two, right? So and if you see the the formula for how to estimate this TPHL and TPLH, you can see along with CL the total load capacitance. You also have one equivalent resistance, right? So regarding that equivalent resistance, how to estimate that equivalent resistance? So for example, we have started the discussion, but I think we could not finish it because of lack of time in the last class. So you can see, for example, say this capacitor is the CL capacitor, load capacitor CL. This has been fully charged from 0 to VDD, right? And when it has to discharge from VDD to 0, right? But we calculate the propagation delay when the output is does a transition from that VDD by 2 point, right? So considering that fact that propagation delay is associated with the 50% change in magnitude in the output, right? So you can say that we can estimate the average resistance, okay, of any transistor from its ID VDS characteristic. So for this ID VDS characteristics, you need to plot this this ID VD characteristics for when again for V. Okay, obviously you should know that at what gate voltage you should plot it. So gate voltage would be equal to the VDD, right? So at gate voltage equal to VDD, you should plot this IDVD characteristics, and then when this VDD equal to this means VDS equal to VDD, then the resistance is given by right this. Hmm. And when this is VDD by 2, this VDS equal to, then the resistance can be given by this, right? It is basically this V by I, right? So if you take the average between this, right, so that would give you that resistance, okay, average resistance or the equivalent resistance. And you can actually estimate that resistance, that equivalent resistance, like this. Say R equivalent would be equal to, so we have to take and this thing, right? So okay, let me take it like, keep it like this. So you have to take an average, like average from here to here, right? Okay, how do you calculate this resistance is nothing but V by I. All right, so okay, so let us say that what is V is this voltage, right? This output voltage. So this is this V, so let us write that V by what is this current is a saturation current, right? So if it is a submicron device, then we can write this as ID sat into 1 plus delta of V. Again, this V, this is basically VDS, right? And we have to take and like we are taking the average, right? So basically we are summing it up, and then you have to take an average. So average we are taking it from this when the change is from this here to here, right? Changes from this VDD to VDD by 2. So the range is VDD by 2, right? So if you take if you take this, if you know this equation, you know this V, you know this VDD by I, then you should be able to calculate what is the R equivalent resistance of this NMOS or PMOS in this way. And if you calculate, so if you just do this, complete this, then we will get something like this ID sat into 1 minus 7 by 9 lambda VDD, right? So here this lambda is not equal to 0, because you can see here it is not parallel, right? So the short channel effect means the channel length modulation parameter is not equal to 0. So considering that, you can see from here that R equivalent can be written in this way, right? Okay. Yes, let me save this one. So here one
Can you
more
tell the range once more, please?
sorry.
Tell the range of the, I mean, the limit of the integration once more.
Oh, right. Yeah, I need to put the limit. Yeah, you are right. So we are taking this integration from here, this point to this point. Right. So it should be from VDD to this VDD by 2. Right. Right. Okay. So here you can see from here that R equivalent is inversely proportional to this ID sat. Right. Again, this ID sat is proportional to W by L. So if this L is constant, okay, for a particular technology node, then you can say that this ID sat is proportional to W. So that way you can obviously say from here that this R equivalent is directly proportional to 1 by W, right? So remember this relationship, right? If you increase this W, right, the width of the transistor, this resistance will decrease proportionately, that in this fashion, right? So from here you should be able to tell suppose you need to change the resistance of some transistor, okay, for a some different application, then you should be also able to correlate what is the relation between the resistance offered by this transistor and its width, right? So what about VDD? Can you make any comment? What about VDD? Any comment on VDD?
So why are we obtaining resistance by integration?
Sorry?
So why is resistance obtained from integration? Shouldn't it be dV by di?
Because, okay, we are actually what we are doing here, we are actually taking this thing. Suppose this is one resistance, okay. Suppose if you are calculating here from this one, right? IDPT one resistance, here one resistance, right? Then you can average them, right? Or you can think like you can calculate one more point here, one more point here, one more point here. Right. So if you want to see that what are the total this thing, then that is why we are doing this integration. Basically, what we are doing, what we are taking, this is this V by I only, right? So we are like summing up all the resistances from here to here, and then averaging out,
Okay. So,
right?
why can't we do it with the derivative? Like,
Yeah, please suggest how.
so like dV by di.
dV by di. Okay. So how do you do? How are you planning to do that? This delta VD by delta I.
Yes, sir.
Yeah.
So I is the
So
function of
if you
dV.
are taking derivative, then it would be at a particular point only, isn't it?
Yes, sir.
Right?
So
Right.
won't it be same for the whole saturation part?
No, you can see that, right? It is not the same. Suppose if you are calculating the resistance at this VD, so here the resistance is given by this value, right? This delta VD by this ID, right? If you are calculating at VDD, then this value has changed,
Yes, yes, sir. Yes.
right? So it is continuously changing. So we are taking some average anyway, like we are here
Okay.
also doing some approximation, right? It is not that exact or correct value, right? But this is for
So
hand
I think
calculation.
derivative will give us the dynamic resistance.
Derivative will give us the dynamic resistance, right?
Okay. Yes, I got it. Thank you.
Right. So you understand then what is the relation between this R equivalent, and then this W. Now, what about this VDD, like VDD? What do you think that how this VDD will impact?
So like since VDD here is in a square relationship and downward facing parabola type curve,
Right.
therefore up till the middle point where it attains the maxima, we can find an increase in resistance, and after that it will decrease.
Right, right. So if you actually plot this one from simulation, so you will see it basically comes something like this. So if you plot R equivalent of say here we have plotted for NMOS. Okay, so if it is for NMOS, then it would come like this. Okay, when this VT is close to equal to VDD is close to equal to the threshold voltage of the transistor, then there would be a sharp increase. Okay, then there would be a sharp increase. Beyond that, you can see the resistance is all more or less a type of flat, right? It's not that way dependent on this VDD. So remember these characteristics, and I hope that if you consider like as your friend like discussed, so from the relationship itself, you can also like guess like what should be the nature of that, right? So you can see that then what is the relation between R equivalent and VDD? Right? Okay. Now, to give you some idea, like what would be this value for a particular CMOS technology node, let us consider this CMOS 250 nanometer technology node. Okay, so 250 nanometer technology node CMOS means here gate length is equal to 250 nanometer or 0.25 micrometer, right? Okay, so for this technology node, what is the supply voltage VDD? Supply voltage is equal to 2.5 volt. Okay, TOX oxide thickness is 7 nanometer. Okay, just a few values. Okay, no need to remember all these things. Like just for maybe later on we can compare with different technology node. Then there you will understand it in a better way. And if you see the values, okay, these two tables are from your book that Niemann, not Niemann. This 1 minute. I think from this rabbit. Right, from this Rabbit's book. Okay. Now, if you see this, these are for the same technology node. Okay, 0.25 nanometer, 0.25 micrometer CMOS technology node. Okay, for minimum gate length. So minimum gate length is suppose for a particular technology node, they will mention like this can be the minimum gate length, right? Say for here like okay, uh, here it is 0.25, like this is the gate length, right? And here this minimum gate device means basically, sorry, it is not the actually the length, minimum length device, it is actually should be the minimum width of the device. Okay, what should be the this characteristics? Okay, for example, here also you can see when this W by L is equal to 1, that means when you make the length and width of this of a PMOS or NMOS equal to 1, right, or 1 unit or the equivalent same, right, then what would be the like resistance and all this parameter. So let us see a couple of values. For example, what is this VT naught? VT naught is the threshold voltage of NMOS and PMOS, right, when you do not consider any short channel effect. Okay, then the threshold voltage of this NMOS is 0.43 plus 0.43, threshold voltage of PMOS is minus 0.4, right? These are the gamma values. Gamma values, I hope you can recall. This gamma values is this body how the body bias will affect the threshold voltage, that parameter, right? Okay, this VD-SAT, I hope this also you recall. This VD-SAT is this voltage, right? This voltage is this VD-SAT. K dash, I hope this also remember. This is the that initial part. I like in this the technology parameter part. Okay, in the equation, this is that one. Lambda is again the channel length modulation part, right? So important thing is the threshold voltage. Please do remember the threshold voltage, that they are more or less the same, and one positive, one negative, and in the these are in the range of 0.3, 0.4 to 0.45 in that range. right? So if you see the equivalent resistance, okay, when W by L equal to 1, all right, then you see for NMOS, okay, this is in kilo ohm resistance, this is this is 35 kilo ohm and 115 kilo ohm, okay, respectively for NMOS and PMOS, okay, and this is when the VD equal to 1. Okay, now say we are changing this VD to 1.5. See, this has decreased from 35 to 19 and this has decreased from 55, right? Then from 2, when this VD equal to 2 volt, then we are making this from 19 to 15, then 35 to 38. So you can see the gap, this gap has reduced, right? Even though the change in VD is almost the same. Now from here to here, see the gap has even reduced. That is basically also you can see from the same diagram here, right? Right. So these are the important values for us, right? For example, for NMOS for 2.5 VDD, the resistance would be in the range of 113 kilo ohm when W by L equal to 1. Okay, and for PMOS, this is 31. So you can see what is the ratio of resistance between NMOS and PMOS, right? So it is basically Rp by Rn would be equal to 31 by 13. So this is the ratio. And obviously you can see this ratio is actually more than 2, right? So from this you can also guess what should be the width of this PMOS and NMOS to make the VTC symmetric, right? That is also you can guess from here. Okay. And even if you change the technology node from 0.25 to suppose some different technology node, then this value is not going to be the same. This value is again going to be the change. Even the ratio will going to be the change. Okay, so this ratio is quite dependent on the technology node that you are using. Okay, and please do remember one thing while we are calculating like how this R equivalent is dependent on VDD, or for example on this table. So when you are plotting, suppose this we are considering VDD equal to say 1.5. Okay, then at that time we will be taking, okay, for this case we will be taking ID and VDS. This VDS is VDD 1.5 volt, and here VGS would be equal to also 1.5 volt, right? Because if this VDD supply voltage itself is 1.5, then VGS also have to be equal to 1.5 only, right? So please do remember that if it is 2, then like you have changed it to 2 volts. Yes, Alisha, I can see that you have raised your hand. So do you have any question?
Yes, sir. So could you please explain the R equivalent versus BDD graph that you've drawn again, because it doesn't match any of the expressions we derived earlier.
In any of the,
Like we got the closed form expression, and that was a downward parabola, but this doesn't resemble a downward parabola in any region. So
yeah. So here have we not done some approximation in this? And here while we are saying this VDD, probably you have only considered this value VDD. Does VDD also there in some other place, somewhere else? What
I
about ID SAT? Does it not have any impact of this VDD? It does,
yes, sir.
isn't it?
Yes, sir.
Right.
Thank you, sir.
No issue. Yeah. So I hope that you have understood the basics, right? How the what should be the nature and how this R equivalent is dependent on VDD, and the most important thing is the width, and what would be the practical value like for a particular technology node, for a 250 nanometer CMOS technology node. Right. So now let us discuss something which is a bit interesting from here. That is, the propagation delay from the design perspective. Okay, so for example, say this is one inverter, say this is another inverter, right? And they are type of like identical, okay, in nature. So same with for here PMOS, NMOS means PMOS here same with NMOS here the same. Okay, now let us focus for the first one. Okay, so for the first one, how do you decide the ratio of this NMOS and PMOS? Just now we have discussed based on the resistance, right? Because we want a symmetric charging and discharging, right? So that is what we want. Like when it is charging, means suppose if you have a load capacitor here, right? So when the load capacitor is charging, right, this CL is not changing for charging and discharging. Only thing that is changing is the this transistor. So during charging it will be the resistance of this PMOS, and during discharging this would be the resistance of this NMOS, right? Charging and discharging, right? So depending on that, we have seen basically we have to make the PMOS and NMOS ratios accordingly such that their equivalent resistance would be the same, right? But that is from what perspective? That is from the symmetrical VTC and symmetrical charging discharging, from that perspective. But that was not from the propagation delay perspective. That means if you take the ratio, for example, take this 2:1. Okay, even though that 2:1 ratio can make this charging and discharging that cycle symmetric, but that does not guarantee that you, for this criteria, you are getting the least propagation delay. What I am trying to say is that now we have to try to find what should be the ratio of this PMOS and NMOS such that the propagation delay of an inverter would be minimum. And I will show you that this 2:1 definitely that is not the ratio. Okay, or the means the ratio of their equivalent resistance. Okay, this should not be the ratio to get the minimum propagation delay. So but before that, let us write here a couple of things so that you can understand it later on. So what about the ratio of this NMOS and PMOS? Like so far what we have considered, we have considered PMOS transistor has to be wider, right, than this NMOS, right, such that pull up network and pull down network resistance matches, right? This was our like whatever we know. But if this is not from the definitely this is not from the propagation delay perspective. Okay, from propagation delay perspective, we can get a better propagation delay if we change this ratio not to as per like the resistance point of view, but some different point of view. Okay, so for that, let us consider that let us say that let me delete it. Huh? Let us say that this inverter, these are identical inverters, and this inverter is driving this another identical inverter. Means the same inverter it is driving. So this is the V in and this is the V out 1. This is the V in 2 then, and this is V out 2. Okay.
It's not visible. Can you scroll it a bit?
Do you have any
The
question?
inverter part.
Huh?
The inverter wasn't visible when you were changing it.
Sorry, what is not visible?
The inverter part, like the drawing of inverter.
Inverter is not visible?
No, like just scroll it a bit.
Okay, now?
A little more.
Hmm?
Yeah, fine.
Oh, is it? So, but for me, I am seeing like couple of places which is blank, like in the top.
Sir, in my computer it's visible.
Yes, I think Balakrishna is like zoomed it. Like,
Yeah,
Oh, okay.
sorry.
Yeah,
Yeah,
yeah.
sorry.
On
Sorry.
phone
Yeah,
he
maybe
might have zoomed
Balakrishna.
it.
Yeah, because
That's
if I
fine.
keep it
Yeah.
like this, then I cannot probably write it below. Okay, so please check. Is it visible now, Balakrishna?
Yes, sir. Yes, sir. Actually, I zoomed it.
Okay, fine, fine. So, okay, so okay, so from the from to now, because now we want to get the minimum propagation delay, right? So this is our now the main motivation. Okay, so for that we have to consider what is the total load that has been seen by this first inverter. So when you consider the total load, that means we have to consider the load at this V out, right? So load at V out 1. Okay, so please check. I am writing something, and please check if this is correct. So this is I'm writing it like this, that this total load at V out 1 is equal to this output C output 1. C output 1 is the equivalent output capacitance, equivalent O out for output, P for PMOS, equivalent output capacitance of PMOS. Okay, let me first write it, and then because here some nomenclature we are like we are doing some different nomenclature. So CP2. So here, I think you can easily understand from now here. So what is this V output? This VOP1. This is P1 means this is the first inverter. 2 means the second inverter. P means this PMOS. N means NMOS. Then O for this output. Okay. G for this gate input. So what is this VOP1? This is the equivalent output cap of PMOS. What is this CON1? This is the equivalent output cap of this NMOS. Right. What is this CGP2? GP2. This is the gate capacitance, means total gate capacitance, right? Input gate capacitance of this PMOS. Input gate cap of PMOS. So similarly, I'm not writing here. This is the input gate cap of this NMOS. This is the wiring capacitance. Right? This is the wiring capacitance. So clearly, this part is from the first stage, and this part is from the second stage. Right, I think the same thing we have also done it, like just we are changing this notation so that it would be easier to represent. So here because this is the same thing actually. So this is the C out 1, that means the total out capacitance at this node 1. So this is basically C in next, right, and C wire capacitance and C cell. This is the cell capacitance, right, the self loading effect, and this is the total capacitance. So the exact same thing we are writing there, but we are using not writing in this way, because then it will be difficult to write such a big expression again and again. So a couple of things we are combined, and we are writing like in this fashion. Okay, right. So and let us also assume that PMOS width is beta times that of NMOS. Okay, so yeah, you have to be careful. Sometimes I'm writing small n, sometimes I'm writing capital N. Okay, so it is so say this PMOS width is beta times that of this NMOS, right? So that means basically what that means, we can write definitely this thing, that beta is the WL ratio, W by L ratio for this PMOS by W by L ratio for this NMOS, right? So if it is true, means if it is if it holds, means if we have set our design like this, right, then can we not write this v, yeah, can we not write the CL here like this, CL? So it is COP1, right? So our goal is to write everything in terms of this now NMOS. Okay, so see, if the transistor means if this PMOS is of beta times the width is beta times that of this NMOS, then all the capacitances that are associated, okay, that would be also beta times that of this NMOS. So NMOS capacitance, if it is output capacitance or self-loading capacitance is CON1, then can we not write this COP1 as beta times of CON1, right? So we are just writing it like this, because if you can check, if you check that all the self-loading effect means the capacitance that is associated to the self-loading, okay, if you change the width or increase the width, that capacitance will also change proportionately or linearly, right? And then plus this CON1, right? Okay, so this is that first part. The second part, similarly, this capacitance, the input gate capacitance, they are also linearly proportional with the width. So here also we can write this beta times of CGN2 go plus this CGN2 plus this CW, right? So here, because why we are doing this, you will understand. So 1 minute. This is CGN2 plus CW, isn't it? So this is the total capacitance. Now we can see everything we have represented in terms of this NMOS. Okay. Now our goal is to find here the minimum propagation delay, right? The minimum propagation delay. This is the goal, right? So for that, CL is the one component. The other component is the R equivalent, right? So let us write that part. So what is R equivalent? R equivalent is the R equivalent of this N plus R equivalent of this PMOS, right? Okay. Can anyone tell me this N and P represents which NMOS and which PMOS? This NMOS PMOS or this PMOS NMOS?
So the first one,
The first one, right? Because we are considering the charging and
discharging
discharging
from
of
them.
this. So this is the first one. Even though they are identical, so they should be same. But right now we are considering the charging, of this, like this node, charging and discharging. So obviously we are considering this PMOS and NMOS, this NMOS, right? Okay. Now suppose here too I want to change this R equivalent P, or I would like to write R equivalent P in terms of R equivalent N. And considering this, how can I write it?
So 1 by beta type.
1 by beta.
1 by beta, definitely, right? Because just now, today only we have seen this, right? So we can write it as R equivalent N plus R equivalent N by beta. I think let us not do it like this. then it would be a bit tricky, like for the analysis. Let us change the analysis little bit from here. See, we are writing this R equivalent, right? Okay, up to this part is same, but we are writing n as like this, n only. Okay, but we are changing only on small definition. The small definition is like this: if this is a PMOS, okay, and width equal to this one, okay, let me put it in this way. Say this is NMOS and here width equal to 1, right? These resistances are equivalent N. These resistances are equivalent P, right? But for our case, we have considered that here width is equal to beta, right? Then what would be the equivalent resistance of this? So please check if you agree with me or not. So what I'm saying is that if it is NMOS and width having a width of equal to 1, and if these resistances are equivalent N, okay, fine. Then in the next argument I'm saying that again for the same width, that is width W equal to 1, if it is PMOS, then obviously its resistance would be different, right? It is R equivalent P, fine, right? But as per our definition or as per our assumption, like we have taken P width beta times that of this N width. So considering this, okay, so now the W is equal to this beta. If this is 1, then it's beta. Then what would be the equivalent resistance of this PMOS? If for unit width it is R equivalent P, then for width beta it would be R equivalent P by beta. Is this part clear to you? Maybe like one of you can respond, otherwise like stop.
Yes, sir.
Okay. So it is, so we are just writing it like this. Fine. Okay. We could have done the previous way as well. Then the entire thing would be like a bit like the equation would be a bit different. Okay. So I just wanted to follow this notation. So yeah, basically we're doing the same thing only, but we're just writing it like this. Okay. Then what is the total propagation delay? Total propagation delay, we know that it is 0.69, right, into TPHL plus TPLH by 2. TPHL TPLH by 2, right? So that means definitely we can write, I think we don't have enough space here, so let me write it below. So it is 0.69 by 2, right? Okay. So now what we have to do, we know this capacitance, we know the resistances, right? And if you just like multiply this one with this equivalent inside, then basically you will get TPHL plus TPLH, right? We are basically doing the same thing, just kept these two outside and we are multiplying this. C1 this CGN2 plus CW, and here we are writing this R equivalent P by beta, right? So anyway, I think if you do it, it would come some value, but let us this is not important as of now, so let us keep it like this only, and let me write it like this. So it is 1 plus beta. Okay, let us keep it like this only. Okay, then why I'm writing it again? CW. Okay, here let us do represent it like this, that I would like to write it like this: equivalent N, R equivalent N, just taking this common, plus 1 by beta, okay, into here R equivalent P by R equivalent N, right? Okay, just wanted to write it like this. Fine. Okay. So this is TP. Now, if I say that, let us say, let us write R is equal to R equivalent of P and R by R equivalent of N, right? Then, could you please say, like, what is this R? What is this R? If this R is the equivalent, means this is the ratio of this like equivalent resistance of P MOS by equivalent resistance of N MOS.
WN by WP.
Huh?
WN by WP.
WN by WP. Are you means? Is it correct? Because how have we defined here R equivalent P? R equivalent P. What is the width? If the resistances are equivalent P, what is the width of the transistor? 1. Then does it correct? Like what you said, like R equivalent P by R equivalent N would be equal to W, like
Be 1.
huh?
1.
It is basically 1, right? Right. So basically this is the ratio of resistances of identical PMOS and NMOS. Right? It is basically the resistance of identical PMOS and NMOS. So it is not the ratio of actual PMOS and NMOS. Okay, but let me let me tell you something here. Okay, suppose this is PMOS, this is NMOS, and you have a load capacitor here, right? And you have a VDD here, this is V in here, this is V out here. Now I am saying if this width is equal to 1, if this width is equal to 1, both width, then its equivalent resistances are equivalent okay, let me not write R equivalent this one, let me write here it is like, okay, say it is of like 2R. Okay, let me write it like this. Say resistance is equivalent resistance is 2R. Here the equivalent resistance is R, right? Then if I have to get a symmetrical VTC or a symmetrical charging and discharging characteristics, then what should be the ratio of this PMOS and NMOS? Is my question clear or like not clear? Yeah, Akshay Jain. Akshay, is my question clear to you? I don't know whether Akshay is present or just. Yeah, what about Arsh?
Yes, sir, I'm thinking.
No, is this question clear?
Yes, sir.
Yeah, so could you
I'm
please
just
tell the question in your own words?
so uh, I'm still thinking about the previous resistance part.
Sir, here WP equals to 1, WN equals to 1, but the resistances are different. Is this due to the VDD? I mean, the VDS across the two transistors are not same. That's why.
Yeah, no, Shubhan, is it not correct that for PMOS the resistance would be higher for suppose if you take the same width, then for PMOS the resistance would be higher because of lower mobility of holes,
Okay, okay.
isn't it? So for PMOS the hole is the carrier, na?
Yes.
So mobility is lower, right? If the mobility is lower, then the resistance offered by that transistor would be higher, right? So that way, so when you are taking the same width for PMOS and NMOS, we are getting this resistance. Okay, here 2 R and here R. So that means we are assuming that this transistor, like the whole mobility, is half of electron mobility, right? But my criteria is that I should get a symmetrical charging and discharging time. That means the charging time and discharging time should be same. So considering that, you tell me what should be the width of this PMOS and NMOS so that you can achieve that. It's a very simple question.
WP equals to 1, WN equals to 2.
WP equal to
1, WN equals to 2.
how? See, okay, what you are saying, if I write it like this, so you are saying WN equal to 2, right? So when you make WN equal to 2, what would be the equivalent resistance of this transistor? It would become R by 2, right? But you are keeping WP equal to 1, that means its resistance would be 2R. So while charging, it will see the resistance of 2R, while discharging, it will see a resistance of R by 2. So it will not even be, the symmetry will be even worse than the previous case. Shubhayan,
Yes, yes, sir.
have you understood?
Yes, it would be
Yeah, then tell me like what should be the equivalent, means what should be the correct answer. It's not difficult, I do not know.
So
WP.
make WP2.
Right, you have to make WP, you have to make WP equal to 2, and what about W1?
Keep it 1.
W1 should be equal WN equal to 1, right? Because when you make WP equal to 2, this resistance would become R, and this resistance is for WN equal to 1 is R. So while charging, it says the resistance R, while discharging, it says the resistance R, right? So that way, charging and discharging will be symmetrical, isn't it? Right. So to get a charging and discharging symmetrical, please notice that what you are doing, you are basically doing like this. You are taking WP by WN ratio. Would this is equal to RP by RN, where RP is the resistance of PMOS for WP equal to 1. Rn is the resistance of NMOS when Wn equal to 1. Please tell me who have not understood this part. Please tell me who have not understood this part. This is important, okay? This is again and again, this will be coming again and again. If you have any doubt, I can explain it in a separate page. That is not an issue. Again, I am not getting any response from your side. Yeah, what about Orithro? Orithro Gangopadhyay?
Yes, sir.
Yeah. Have you understood Orithro?
Yes, sir. Yes.
Okay. Deepak?
Yes, it's fine.
It's fine? Okay. So Then let me just repeat it again. If you want a symmetrical charging and discharging characteristics, then you have to take the width of PMOS by width of NMOS equal to, this would be the ratio of this Rp by Rn, right? Then from this discussion, can you please tell me what is this R? If you have understood this part, then you should be also able to tell me what is this R.
WP by WN.
This is
WP by WN.
this is again you are saying same thing.
So
No,
is it like
Subhayon, it is not WP by WN. WP, see here, it is, you are saying it is WP by, okay, you are saying it like WP by, this is WN. But WP is of beta time, that of WN. Is it
So,
correct?
okay, sir. I mean, when this
Right, it is
both are
like, this is right, this is when, I do not know why this part is not clear. See, this R equivalent P, this is when PMOS width is equal to 1. And this is when this NMOS width is
equal to
equal to 1. Isn't it right, Shubhayan?
yes, sir. Yeah,
Right,
that I want.
right. So, what is this R then? From charging discharging point of view. This is the R, okay, or this is the factor by which so far we have designed our inverter, right? If this R is equal to 2, then for an inverter we have always made PMOS equal to 2 times, the PMOS width equal to 2 times compared to that of this NMOS. Not clear yet? I do not if you do not tell me how will I understand that whether you are understanding on this is online, right? Even I am not able to see that, your eyes and able to get a feedback. So if you have to, then only the way that you can communicate is by saying something, right? Now, but if you do not communicate, then how I will understand that you are getting it or not? Yeah, Alicia, have you understood this part?
Yes, I think so.
You have understood, right? Okay, so if I make this PMOS R, the PMOS with R times that of NMOS, so can you comment what would be the relation between charging time and discharging time, or TPHL and TPLH? Yes, this question is for Alicia.
If you make the PMOS with R times, right?
Yes.
Okay, if you make the PMOS with R times, then that R equivalent will become 1 over R times compared to the NMOS.
Hmm.
Which means that the charging time for PMOS is charging time. Yeah. So the charging time will become 1 over R times compared to the discharging time. So TP charging is high to low, probably.
Are you
Yes.
but Alicia, I am a bit disappointed, like why you are saying so. Again, okay. See, what is R? Please tell me, Alicia, what is R? It is the equivalent resistance of a PMOS having width equal to 1 by NMOS width for NMOS whose width is equal to 1. Right. Now what I am saying, I'm just saying that you make these R times then that of this NMOS. Okay. Now you tell me what is the equivalent resistance of this?
So we are changing the width, right?
We are changing the width.
Okay, yeah.
We are changing the width. So, okay, let me tell it. Suppose this resistance is equal to R. Okay, then what would be the resistance of this?
Sir,
R same.
R. Okay. Oh,
R. This is R,
sorry.
right?
I didn't realize you were keeping that part same. Sorry. Then they'll be same.
Right. So this is R, this is 1, right? We have, that's what I said, like we are making PMOS R times compared to the NMOS, right? With, so it is R, it is also R. Then that will basically give us the symmetric charging and discharging. TPLH and TPLH and TPHL should be equal, be the same, right? So that is what motivated us earlier, right? So earlier we have always kept PMOS width by NMOS width equal to R, right? But now we are thinking it from bit different perspective. Now our perspective is that we should get a propagation delay which is minimized, right? So for that, what should be the ratio, or what should be the value of this R, or what should be the criteria for that? Okay, so see here, so far what we have derived is that TP relation is this. Now we have said like this is R, then what we can write? Then TP equal to, just let me write it again, 0.69 this into 1 plus beta, and here C1 and here Gn2 plus this Cw, and here this R equivalent N, and just write here 1 by beta and just write here R, because we are just I'm replacing here R, this one, nothing else. Okay, now we should know for what value of R TP, right? TP, or sorry, not actually the what value of R, but for what value of beta, right? The TP, because beta is the beta we have taken here, right? This is the actual width that we have considered for this design. So what value of, for what value of beta we should get this TP minimum? So we know one technique that we have used many times. So we will do a derivative of this TP with respect to beta and set it equal to 0, right? And that basically that would give us the criteria for our minimum propagation delay. So if we do that, then we will get this optimized value of beta, or the expression of this optimized beta, something like this: 1 plus the CW CON1 plus CGN2, right? So please do this, make it equal to 0 and see that whether you are getting this or not, right? Now here one simple assumption, and that would make we can actually take much more or conclusion out of it, is when CW is much lower, means the wiring capacitance is much lower than the these two capacitances, like the output capacitance of NMOS and the gate capacitance of this NMOS. When this is very less, then this part can be neglected, and then you see this beta optimized would be nearly equal to root over of R. So please note, this is very important, right? This is for minimum propagation delay. So please note, when you make beta equal to R, you get a symmetric charging and discharging, right? But this is not the criteria for the minimum propagation delay. For minimum propagation delay, the criteria is somewhat like this: that you have to design PMOS with root over of R times that of NMOS. Say for example, okay, say for example, let's say this is 2R, okay, this is R, right? then making this WP equal to 2 and WN equal to 1 would give you the symmetric charging and means symmetric charging and discharging, right, profile. But making WP equal to root over of 2 and WN equal to 1 would give you the minimum propagation delay. Fine. So this is the important understanding. Please keep it in your mind and note that whenever you are doing that 2:1 depending on the mobility and all these things, please remember that that is from the symmetric charging discharging point of view, but that is not the criteria for minimum propagation delay.
Sir,
Huh.
sir, I had a doubt like what's the condition that we aim for while designing a circuit, like the minimum propagation delay or symmetric one?
That again depend on your design problem. Right. Sometimes even the propagation delay does not play that much role, but the power will be the most important significant parameter. Right. So this is between like what you get and what you means what you take and what you lose like that.
Okay, sir, got it.
Right.
So,
Yeah.
so why we are considering propagation delay as average, like it's in general questions, because one of them would be lower and one of them would be higher.
Yeah, one of them would be lower, one of them would be higher. True, because see, when you are considering as a gate, right? Right, as a gate. So sometimes at input it would be higher, right? Sometime at input it would be at logic 1, sometime at logic 0, sometime, right? Then
Yes.
how do you right? Then like as a total thing, like if you give 1, if you give 0, then what should be the delay? So that basically give one like ideal condition, right? I mean, ideal condition is ideal understanding. Okay, this gate behaves like this gate, particular gate behaves like this.
So I
And
mean,
that,
suppose like TPHL is greater than TPLH,
hmm,
but TP would be less than TPHL because it's average.
right.
So till then, it won't be like it hasn't been decreased from high to low if we consider TP. So won't shouldn't we consider the like maximum of two?
Shouldn't be consider the maximum two, but we are considering the average of them.
So I mean, like if we consider general gate, like till then the output won't come low if we consider TP,
Mhm.
if TPHL is higher than TPLH. It would still be greater than 50% of the maximum difference, right?
Yeah. Yes. Yes. See, it is something like this. Okay, let me first tell this. Okay, in this context, and then I will come to your question. Okay, then it will be easier. Let me see. Yeah. Okay. So, for example, okay, if you do a simulation and just plot this TP versus beta. Okay, now you know what is the beta. So beta is the ratio of W by L for P and W by L for N, right? If you plot it, then you see for a particular technology node and say around for 2.5, okay, around 2.5 you are like getting this one. So what is this one? Please note that here this the value of TPLH, TP high to low and TP low to high and TP high to low, these two values are same. But definitely this is not the minimum propagation delay, right? So because minimum propagation delay is been considered as like I was discussing, it is basically the average of these two, right? So minimum propagation delay is not at this point, but rather somewhat at lower point. So if you consider this as R, then you will from simulation you will find this value would be close to near about this root over of R. So here the propagation delay would be minimum. Okay, now here one important thing is that you see as you are increasing the value of beta. So as you are increasing the value of beta, that means what you are doing, you are basically increasing the PMOS width. So when you are increasing the PMOS width, so PMOS width you are increasing, right? So basically you are increasing this, right? And PMOS helps in charging. So PMOS helps in charging. So as you are increasing this PMOS width, right? So what will happen to the charging time of this capacitor? The charging time of this capacitor, right, as it can conduct more current, so that would be significantly reduced. So as you can see here, right, TP low to high. This is low to high, right? TP low to high is keep on falling as you are increasing the value of beta. On the same token, you can also and see that if you increase the value of TP like beta, then again here this TPHL, that value should rise, or in other way, if you keep on decrease the value of beta, all right, then this value should fall down. And at this value, right, R, these two would be same, all right, but this is not the minimum propagation delay. Minimum propagation delay would be if this value is R, then somewhere at nearly equal to root over of R, right? Now yes, your question is should we not consider the maximum of this or maximum of that? Yeah, we could have considered that, but see what makes more sense, what makes more sense is that as a gate, suppose if it is an inverter, right? So is it good like what should be the maximum? Okay, suppose sometime we are giving at logic 0, sometime we are giving at logic 1, right? So depending on that, that output TPHL and TPLH may be significantly different. Then you have to always keep in mind, right, that TPLH is this, TPLH, TPHL is this value. But rather, if you define TP or propagation delay such that it is average, and then in your design you always also try to maintain this thing that this TPHL is equal to TPLH, right? Then that problem somewhat be solved. For example, here, if you consider this, so here as it is the average, right? Or if you consider maybe here this, for some particular value of beta here, or some particular value of beta, then here TPLH and TPHL is not that way significantly different. But if you consider some extreme design, for example, here, so here you can see TPHL is extremely high, but TPLH is extremely low. Probably this is not anyway good design as well. Okay, so good design would be where the the CPLH and TPHL, they are quite close, and for those design, making taking TP as the average value would make more sense compared to knowing the extreme values, because they are almost the similar, right? Yes, Hare Krishna, is
Yes,
that
I, yes, exactly. This was my doubt. Like before, because when we were going for minimum propagation delay, so TPLH is significantly higher than TPHL.
right? So
Like in the
is it
middle, it's all right. Yeah.
yeah, okay, okay, thank you. So I hope with this you have understood like what should be the what will happen if you take beta equal to R, and what will happen if you take beta equal to root over of R. And I hope that you have understood what is R. That is most important. Okay, if so, then probably we can go to the next discussion, which is quite interesting. See this. Uh, Sizing an inverter for performance. Okay, now we have suppose on one inverter, okay, here one inverter, okay, and here some load, say CL. Now this inverter, maybe you can keep W by L ratio for PMOS say 2, and for NMOS equal to 1, or more for PMOS W by L 4, for NMOS W by L equal to 2, right? So how does that sizing, okay, like from earlier, from the first one to the next one, we have just double the transistor sizing, right? How does that impact the performance? Performance means here we are considering the delay performance. Okay, later on we will also consider the power. So here we should understand, like we have also seen already, just to have a recap, like total capacitance, like it is not actually the CL, it is so I should write here the C external. So total load capacitance here, CL, that is equal to the C internal capacitance plus or not internal, this is basically intrinsic. Okay, this intrinsic, better to say it as, because this is due to the self loading, so it is the intrinsic capacitance, means you understand, right? So if you have an inverter, right? We have seen this inverter itself, these capacitances, these drain capacitances also load this output, right? So this capacitance is the these are capacitances are this C internal or C intrinsic capacitance, okay, or these are the self-loading capacitances. And this is the C external. C external is the external capacitance if it is driving a single capacitance, or if it is a driving another gate, or maybe two gates, right? So depending on that, in general we can say this is because of this fan out, right? So this is basically for this fan out. You are, I think you know what is fan out, plus this wiring cap, right? And this self capacitance is basically the diffusion cap plus gate to drain overlap capacitance, right? This is how we have discussed it couple of times, but just wanted to say it again, recap here. Okay, now see, we have also seen that TP, total propagation delay, we can write it like this, 0.692 R equivalent. Now we are saying that this is the equivalent resistance, okay? This is the equivalent resistance, because now we are not considering what, okay, let me put it like this. C internal, C external. So R equivalent is equivalent capacitance as of now. Okay. So, and here we will write it like this, R equivalent. So we will take this C out, C in outside, and we will just express it like this. Okay, so TP, see what I have written here, TP is equal to TP naught, right, into 1 plus C external by C int or C intrinsic, right? So here what is this TP naught? TP naught is equal to 0.69 by 2 R equivalent into C int. So what is this? What is this TP naught? See, TP naught is also a delay, right? And if you consider this delay dependence, everything is there. R equivalent is there, like C int is there. And what is C int? C int is due to this intrinsic part, right? Like the say due to the self-loading part, right? So this TP is called the intrinsic delay or unloaded delay. Intrinsic delay or unloaded delay. Okay, so that means what? If suppose this, if you have not connected any load, if you have not connected any load, then also this much delay would be there because of this self-loading or this intrinsic capacitance, right? So that's why we have tried to represent this total propagation delay in terms of intrinsic capacitance into the external and internal, a combination of this external and internal capacitances. Now here comes the fun thing, that is, now suppose we want to size, okay, we want to increase the size, okay. What do we mean by sizing factor is, that means if Wn by Ln is equal to 1 and Wp by Lp this equal to 2, right, then we have made it into S, we have made it into S. So that is what it means by the sizing factor, means we have increased the transistor width by S times. Okay, now if sizing factor is S, then we want to estimate what would be the value of this TP. Can anyone tell me what would be the value of TP? Because I think we have done enough discussion on this. So if you have understood the earlier discussion, you should be able to tell me what should be the value of TP. If we now change the PMOS and NMOS width by or increase this PMOS and NMOS width by S times. Anyone? No? Okay, so maybe let us try it like this. So 0.69 by 2. Anyway, this is not going to change. Okay. So what about R equivalent? Is R equivalent going to change if we size the transistor by S times? Deepak?
Yes,
Yeah. So will it change R equivalent?
yes, no, sir.
Huh? Yeah. What about Neha? Neha, can you hear me? P. Jyoti Prakash?
Sir, I don't think it will change because in the formula it was dependent only on VDD and IDS, and VDD is external supply, it cannot change. And
Is R equivalent not dependent on ID?
yes, sir, I'm coming to that.
Is ID not dependent on W?
Sir, but in ID the formula was like W by L, right? It was
Right,
dependent on
W
the
by L.
ratio.
Right. So what
Okay.
about
Oh,
L? I
sorry.
told you
Yeah,
already
yeah. It will change
for a
actually.
particular technology
Yeah.
node, L is constant. So that way this L is not changing.
Yes, sir.
So what will
So
happen
it will
to the,
change.
it will change. So it will
Yes, sir.
increase or decrease?
Sir, decrease.
Definitely decrease, right? You are making the
Yes, sir.
transistor wider. So you
Yes,
have
sir. Yes.
now more path for the current. So resistance is lower. So that way it would be decreased. And we have already, already I have shown you here, right? So for example, today only I have shown you here. See here, R equivalent. Equivalent is proportional to 1 by W, right? So if you are increasing W by 2 times, right, then R equivalent is going to reduce by 2 times. So the same thing we are doing here. R equivalent would be this. Okay, what about C int? What about C int? Intrinsic capacitance.
S times.
It becomes S times.
So it
Okay.
will scale up
It
by
will scale up. Very good. Okay. It will scale up. Okay. What about then 1 plus? Okay. What about C external? Will it change?
the same.
It will remain the same. C external and C int we have already seen. C int will scale up S times. Right. So then you can clearly see what we are getting from here is that if we scale this inverter by a factor S, then we are getting 0.69 by 2 R equivalent C int into 1 plus C external by S C internal. So what is this? This is nothing but TP naught, this part, right? So we are writing it as TP equal to TP naught into 1 plus C external by S C internal, right? So one very important observation from here is that if you size an inverter by any factor, then its intrinsic delay or unloaded delay is not going to change, right? So we can write intrinsic delay is independent of sizing, right? Okay. Now, some more observation from here. If you make S significantly high, right? If you make S significantly high, then if you make S significantly high, then you can see S factor is here. Then this factor will significantly be a, means it may be then this 1 plus C external, this factor may be less than 1. Then in that case, you can get possibly Tp is nearly equal to Tp naught. That means the total propagation delay would be now equivalent to that of its intrinsic delay, right? Then you might think, then whenever you have any issue, means suppose you have to drive any load, then why can't we use an inverter, okay, which is a very large size, means a huge size inverter, okay, to drive any load, right? Because we have seen from here that when this AC is very large, means the sizing factor is very large, then we have seen this Tp will become equal to Tp naught, right? And we have also seen this Tp naught, this is independent of sizing. This, this intrinsic delay does not depend on the sizing, right? Then what do you think? What might be restricting us in doing so? That why can't in any design we can make an arbitrarily large inverter and make them and use them to drive any output load.
Sir,
Participation.
we
So chip
need
size.
lots of them, right?
Uh-huh.
We need in a particular chip there may be many like millions of not gates. So
Right,
if
right,
we increase the size arbitrarily, it was cause sizing issues. Total
right,
size of chip will increase.
right. So basically you were thinking in terms of area, right?
Sir,
In terms
also
of
power
So also
consumption will be
power.
huge, sir.
power consumption, yes, very good. Power consumption
Uh,
is very good.
Current would increase like with a scale of S.
With the scale, right, right. Okay. And one more thing is that suppose, okay, this is the load and this is inverter, and you can arbitrarily make this inverter large. Suppose in one case. But we have to also remember that there is some gate before that who is driving this inverter. So if you make this inverter pretty large, then this capacitances, gate capacitance is also going to be extremely large, right? And for this inverter, okay, which is just driving this in the next inverter, okay, for this is the huge load, right? So this is another way of you can also think. So that is the reason why arbitrarily we cannot increase the size, even though like from this analysis we can see that if you make this a significantly high sizing factor, then actually it is beneficial for the propagation delay. Okay, how are we doing on time? Okay. Now, here is an important thing. Suppose now we have a chain of inverters. Okay, like that. Suppose n is a number, so it is 1, 2, 3, 4, 5, 6, like that n. Okay, and here for the first gate, the gate capacitance is Cg1. For the last gate, the capacitance is Cl. Right. Then how do you size it? Okay, suppose this Cl is equal to 100 times of, say, so just for example, 100 times of this Cg1. Okay, and there are n stages. Then how do you size this number of stages? Means, is it be one, then is it be two times, or will it be three times compared to the first one? Size means the transistor width. Means here, if for NMOS the transistor width is 1, then will you make 3 times for the next case? or we will make 4 times. Then what about in the next case? Our goal is for this chain of inverter, we need, and for this criteria, means for this CL equal to 100 CG1, we need to have a minimum propagation delay. You understand? So that is we are going to address from here. Okay. But before we discuss that, I think we should also briefly discuss a thing which is important in terms of analyzing this one. That is, which we already know, but just one relation here. That is, you know, um, yes, say this is an inverter, single inverter. Okay, then we have seen that it will also have some this intrinsic capacitance due to self loading, right? So this is connected, which will be connected at this output node, and if you see from the input node, it has some gate capacitance as well as the overlap capacitance. So let us say if we are seeing from the gate, this is CG, right? And if you are seeing from this output node, no external load is connected, then also you will see and capacitance which is C internal, C intrinsic, which is due to the self loading, right? Then for sub-micron devices, so what do we mean by sub-micron? Sub-micron means where the gate length is less than 1 micron. That is called the sub-micron. So for sub-micron devices, it has been observed that C int is equal to, C int is proportional to Cg. Okay, and this gamma value, which is a proportionality constant, can be treated as 1, right? So that means for submicron devices, the self-loading capacitance would be nearly equal to that of this gate capacitance only, right? Then if we consider for the single transistor, then what would be the single inverter, then what would be the propagation delay? That propagation delay we have already seen, it is Tp will be equal to Tp naught into 1 plus C external by gamma Cg. So I am writing here this gamma Cg itself, the complete thing. Now if you consider gamma is equal to 1, then it would become C external by Cg, right? Okay. Now what is this C external by Cg? This is called fan out. Okay. So Tp naught 1 plus and denoted by a symbol F, this F. Okay, so let us keep this gamma as well. So because I want to write here gamma, not want to change right now. So it is basically this one. So then basically there is no point of writing this thing again. So we can keep this thing here, right? Fine. So I hope this is like pretty easy to you. And this where this F, as I told, it is basically the C external by Cg, and this is called effective fan out, right? Effective fan out. So it is the ratio of this external capacitance that it has to drive by its Cg. So external capacitance is this one that it has to drive. Okay. Okay. Now I think we have now sufficient background to analyze this. Okay. So here, this is the input capacitance of the first inverter. Input cap of first inverter. Right? Okay. So in between, like that, we have this so many stages here in, say we have some stages here as well. Say we have three more stages, some intermediate stages in between, and we term them as this is J. This will stage will term as J minus 1. This stage will term as J plus 1. Okay, and here too, the input capacitance, here we will write it as CGJ minus 1. Here it is CGJ, and for here this capacitance is CGJ plus 1. Okay, so typically, if I want to write what is the propagation delay for any stage, say this jth stage, okay, then I can write, definitely I can use the same thing here, right, and write the delay. So it would be equal to Tp naught into 1 plus Cj plus 1 by gamma Cgj, right? I hope this part is clear to you, because if you see from this, it is like Tp naught into C external by Cg, right? So for this gate, that is for this jth gate, the external capacitance is this one. So it comes in the numerator, and in the denominator it is gamma of Cg. So gamma of the gate capacitance of this jth stage, which is Cg of j, right? And so this is for any stage, right? You can just keep it 1, 2, 3, and that will give you for like from this 1 to n any stage. Then what would be the total delay if you want to calculate? What would be the total delay? So total delay would be nothing but summation of all the delays, right? So it is Tpj, where this j is can vary from 1 to n, right? And this can be also written, okay, if you see from this case, right, it can be written in this way, j, so it is actually j. Okay, so it is j 1 to n. Now this 1 plus cgj plus 1 and gamma cgj. Right? Is this part clear to you? Think there is nothing difficult, right? So it should be clear to you, right? Okay, just let me ask you one question. Please tell me the value of this CG CGN plus 1. Yeah, what would be the value of this?
100 CG1. 100 CG1.
100 CG1, or basically CL, right? So let us, in general, it's basically CL. So it is the, because it's the last stage, CL, right? Okay. So if you know the total delay, how do you find the minimum delay? How do you find the minimum delay? You know the total delay. So again, we can use that derivative and make it equal to 0. That technique, right? So for minimum delay, by taking n minus 1 partial derivatives and equating them equal to 0. That means what you have to do, you have to take delta Tp by delta Cg of j, right, and make it equal to 0. Right. So here, if you do that thing, and so I think it is quite clear. Please check it. I'm writing it. Is it clear to you? So if you do this delta P by delta this equal to 0, okay, for any stage, that is say for this jth stage, okay, then you should be able to get this expression. Because you can see the other term would become 0 when you are taking the derivative. Only term associated with this would remain. So from here you can see that CGJ plus 1, this is just one simple thing you need to I think once you understand you will remember it for lifelong. So you see, then basically while you are taking so what should be the criteria for minimum delay? Minimum delay criteria should be that such that CGJ, that is the gate capacitance of jth stage, should be the geometric mean, right? This is called the geometric mean only, right? This is called it should be the geometric mean of its neighboring stages, because n minus 1 was j minus 1 was one of the neighboring stage and j plus 1 is another neighboring stage, right. So that means if you are changing it by 2 times, right, then from here to here also you have to change it by 2 times, right. So that criteria we have achieved, that what should be the criteria of these capacitances, and from these capacitances we can find what should be the criteria of scaling. But still we do not know what should be that number, whether it is 2, 3, 4, 5, 6, we do not know. But so far what we know is this one, that whatever you have to scale, you have to scale uniformly. Now can anyone tell me then what should be that number, like from this, or just tell me how to find that number, right. So far we know that it has to be like 2 times, it has to be 2 times like that, or if it is suppose n times, then next also n times like that. Then how should we find that number? Any guess from here?
So r to the power n minus 1 should be equal to CL by CGI. And from that,
R to the power n minus 1 should be equal to
CL by CGI.
CL by CG1. I think you are in the right direction. Basically, then you are saying we know what is the scaling factor for each case, right? And we also know what is the total fan out, or means what is the CL by CG1. So that way, if you know what is the scaling factor for each, and if we know how many stages are there, then we should be also able to find what should be that factor, right? Right. So then if I write it like this, that F is equal to the overall fan out, which is nothing but CL by the first stage, CG1. Okay. Then what is this F, overall fan out? Okay. See this CL by CG1. So I can write it like this. CL CG2 by CG1, CG3 by CG3 by CG2, then I can write it CG4 by CG3 dot, then I can write CGN by CGN minus 1, then CL by CGN, CGN, right. So you can check it. So this CL by C1 I can write it like this. Okay, and if you, because you can see this is gone, this is gone, like that, with this part will go, this part will go, with this the previous one will go, right? So this basically gives CL by like, you know, this would be C, this would be CG1, right? So basically this is the same thing, right? So and CL by CG1 is nothing but F. Okay, now what is this? The first one is that factor Cg1 by Cg, this, and what is this? This is that scaling factor, that F, right, for one single stage. So that means we are changing by F, right? So that means this part is F, this is F, this is F. So how many times it would be? This n times. So this F is equal to n to the power n. So this F is will be equal to nth root of F. So you know, you understand what is this F? F is that individual scaling. Okay, from this to the next one, from this inverter to the next inverter, from this to this, from this to this, from this to this, this to this. And for all this F, if you multiply, that should be equal to the capital F, which is the overall fan out, which is basically C out, CL by, means the external capacitance by this capacitance, right? So if you know that, so you know now what is the value of F for scaling factor, if you know the value of N. Now again, here is a question, what should be the value of N? Because in any design you can choose any N. I could have done the same thing with 3 inverters. I could have done the same thing using 5 inverters or 7 inverters. How should I determine that what should be the number of N? Okay, I think that we will continue in the next class. But in today's class, I think up to this much understanding is important, that what should be the criteria for minimum propagation delay for a inverter chain, and how to find that factor of scaling. Okay, so this is basically that criteria. So this is basically that criteria for minimum propagation delay, right? And this is the value of that scaling factor. So this basically is equal to F, right? Yeah, if you have any doubt. Okay, no, then I think it's already 12. You might have some other class. So let us end then here today. Yeah, thank you. So we'll meet in the next class.